G. There it is.
That was good.
All right. Anyway. Now, let's talk about chemistry and atoms and molecules and elements and compounds, okay? So here's an atom. Atoms are made up of three smaller thingies. What's one of the smaller thingies that makes up an atom? Benito.
Electrons.
An electron, okay? In this diagram, what's this big hunk of stuff in the middle of that atom called? Kyle? No. Yes. No. Wait, Brandon.
Nucleus.
It's called a nucleus, okay? It's not the same as a cell nucleus, but it's called a nucleus because it's kind of like hanging out in the center like a cell nucleus often does, okay? Now, electrons. Where are the electrons in this picture? Like, where's Waldo? Where's the electrons? Luke.
The thing's flying around.
The things flying around the nucleus, okay? Now, do electrons have a charge? Brandon?
Yeah.
What charge would that be, Robin? They're negatively charged, okay? What's another particle that makes up atoms? Another thingy. Sarah? Protons. Where do protons hang out? Zach?
Yeah.
What's that thing called? Brian knowledge, like 2 minutes ago?
The nucleus.
Nucleus. Protons hang out in the nucleus. Do protons have a charge, Cal? Wrong. Who knows the right answer now? If the first answer is wrong. Cal knows the answer now.
Yes.
Yes, they do have a charge. What charge do protons have? They have a, Mark, positive charge. Okay. Now, one more thing hangs out in the nucleus, and that is called what, Stephanie?
What hangs out in the nucleus?
Soraya?
Neutrons.
Neutrons. What charge do neutrons have? Allegria.
A neutral charge?
They don't have any charge.
Yeah.
They're neutral. Okay. Neutrons are neutral. All right. No charge. They're free. Get it? Anyway, moving on. So this is an atom. If that's an atom, what is an element? What's an element? Robin.
An element is a substance that cannot be broken down to any other substance by ordinary chemical means.
Yes, but the first part of the sentence is that you left out is the most important part. It's a hunk of stuff made up of only one kind of atom. So if you had a hunk of gold, there's only gold atoms in it, that would be an element. So an element is a hunk of stuff that's only made of one kind of element, okay? Technically, you can break atoms up in, separate components like electrons and protons, and sometimes they do lose electrons or protons or neutrons or something like that. But so an element is a hunk of atoms, all the same kind of atom, all right? What's a molecule? What's a molecule? Mark? No. Kyle?
It's multiple kinds of atoms combined.
Yes, it's something where more than one atom are bonded together. It could be the same atom, like two oxygen atoms can bond together, make an oxygen molecule, or two nitrogens, okay? Or it could be different atoms, like a sodium and I can't think what sodium would bond them. Like two hydrogens and an oxygen makes up a molecule, okay? What's a compound? It's a bunch of molecules. So a molecule is to a compound like an atom is to an element, all right? And it's usually a compound is more than one type of atom, or more than one type of element. All right, now that we're done with those bold word terms, now comes the really important stuff that has to do with the periodic table of elements. For the next test, you'll have to memorize all the elements in the periodic table and their atomic number and no. Close your mouth, Robin. I'm kidding, okay? She's going. I said I'm kidding, all right?
I remember I heard.
All right. Shh.
I
Darren's going, oh my God. Kidding, all right? Now, the only atoms that biologists, mostly the only atoms that or the only elements or atoms that biologists care about are in the first 3 rows, and we're going to be talking about some of those right now. All right, so let's look at oxygen. There's a big 8 here. What are these big numbers in the upper left-hand corners of any of these elements on the table there? What are those? What's the name, the generic name for these big numbers here in the upper left-hand corner? Brandon?
Atomic numbers.
Atomic number. And the atomic number of an atom, like oxygen's atomic number of 8, is the number of what that it has? Jonathan?
I'm gonna guess that it's the number of atoms.
No. We're talking about a single atom of oxygen. Its atomic number is of 8. What's the 8 about? What is the number of what that an atom of oxygen has? Chloe? Electrons, but also they usually have the same number of protons and neutrons. So oxygen normally has 8 protons, 8 electrons, 8 neutrons. Okay? Any questions? William?
Wait, you said oxygen normally has 8
Yeah.
of each, does that mean sometimes it doesn't?
Sometimes it does, yes. Okay. There are, what, Luke?
If you change the amount of like electrons, protons, or neutrons, would it make it different?
Yes. Okay. So some atoms sometimes lose an electron or gain an electron, and they become more positively charged or negatively charged. Those are called ions, and we'll talk about those a little bit later. Sometimes atoms lose or have more or less, I think it's neutrons. They all have always, oxygen has the same number of protons, but sometimes it can have more or less neutrons, and I think that's called an isotope, I'm pretty sure. I'm not a chemistry teacher, so I don't know for sure anymore. I used to know when I was like a sophomore in high school. Anyway, just deal with it. Mr. Wenning doesn't know everything. But the important stuff I do know, and that's the stuff we're going to be talking about right now. So, oxygen has 8 electrons, 8 protons, and neutrons normally, okay? So here's the nucleus of oxygen. There are 8 protons and 8 neutrons there, believe me, okay? Now, the electrons are flying around outside on what are called orbits or shells or levels, okay? So, here's an orbit right here. Here's a next outermost orbit. Here's the next outermost orbit or shells. Okay. Does anybody know how many electrons can hang out on the first orbit? Maria?
I think it was 2.
2. 2 are possible. Okay. Does anybody know how many are possible on the second orbit? Mira?
8.
8. And can anybody know how many are possible on the next orbit? Brad?
16.
No. Cal?
32.
No. Mark? No! 8. Okay, I'm gonna stop asking. Okay. 8. Okay. These 3 rows. This can have electrons. These 2 can have electrons on the first orbit. Okay. These can have electrons on the first orbit and second orbit. These can have electrons on the first and second and third orbit. Okay. These have a 4th orbit or shell. Okay. And I think it is 16 or 18. I don't care. I don't know. You don't have to know either. Okay. We care about mostly this stuff. Molecules that are involved in living things. All right. Now, in general, where do electrons like to be? Near the nucleus or farther away from the nucleus? Mateo?
Farther away from the nucleus?
No!
Oh, boy.
What's the right answer? At least we're learning. Joe?
Near the
Near. Why do you think the electrons like to hang out near the nucleus? Cal?
So we can see it.
They can see it.
Because there's like energy.
Kyle?
There's other particles there.
What? are these electrons attracted to in the nucleus? Alegria,
The positive charge of
the protons. They're attracted to the protons. Negatives are attracted to positive, okay? Now, they're not going to go in there and hang out right next to the protons, but they like to be near, okay? They don't like to be out here, but sometimes they get pushed out here, like when light beams hit the photosynthetic parts of a chloroplast, the electrons get pushed to a higher energy level, okay? The farther away an electron is, the more energy it has. It wants to get back here, but sometimes it can't get back here unless it releases its energy, and that has to do with photosynthesis and about using energy molecules that photosynthetic organisms produce. When electrons get boosted to a higher energy level, that's basically what light is doing, okay? Electrons like to be at a low energy level. They like to be here. So, electrons, these 8 electrons for oxygen 8, want to be here, okay, first. So let's put 2 of those 8 electrons on this orbit. How many are left to put on the second orbit? Who can do that now? I know you guys have had dumbed down Common Core. They wouldn't let you take algebra in the 8th grade, but this is not algebra. This could be like a 2nd grade word problem. You start out with 8, but then you put 2 on the first orbit. How many do you have left for the second orbit? Sydney? 6. Okay. And I'm going to put them here in pairs so they're easy to count. Okay? 2, 4, 6. Okay? This diagram here is called a Bohr diagram. Okay? B-O-H-R. And it was created by Niels Bohr, and I think he won a Nobel Prize for, Niels, you don't have to know, okay?
I know he remembered this.
You kind of remember it, prior knowledge? It's coming back though?
A little, yeah.
Okay, alright. Alright, anyway, so for some people it might be the first exposure to this, but this is like real important, so everybody should be paying attention. Alright, now, what makes atoms happy? How many people have heard the phrase, making atoms happy? Or atoms being unhappy? So what makes the atoms happy? An atom is happy when, Isabella or Isabella? Isabella.
When their orbit has 8.
When their outer orbit is complete, okay? It could be this inner orbit, okay? It could be that it only has one orbit because it has 1 or 2 protons. If the orbit is complete, it's happy. The inner orbits don't matter. They get filled up. It's the outer orbit that matters. Is the outer orbit complete or not, okay? Now, here's oxygen. There's 8 possible electrons that can fit on this orbit. Is oxygen happy?
No.
No. It's unhappy, okay? Now, what would make oxygen happy? Chloe?
The element was like 10.
Well, what would make oxygen happy? Forget about the math. Chloe's doing math here. Just look at what would make oxygen happy. Cal?
2 more
2 more what?
electrons.
Electrons. Okay. So this has to do with valence. Okay. The electrons on the outer shell, they're called valence electrons, but that's not valence. Valence is the number of electrons it wants to give or get in order to be happy. So what's the valence number? The number of electrons that oxygen wants to give or get. Somebody just said. Joe? 2. So the valence number of oxygen is 2. Now, valence also has a charge. And the charge for this valence is what it will be, what this atom will be when it gives or gets electrons and becomes happy. So when this atom gets 2 more electrons, is it going to be more negatively charged or positively charged? So math then. It had 8 electrons and 8 protons, and then it gets 2 more electrons. 2 plus 8 is 10, so it has 10 electrons, but only still 8 protons. Is this atom going to be more negatively charged or positively charged? I mean, negative. Okay. So this is not the math symbol plus. Yes, it's adding, or electrons are added to it, But this is the charge, it's not minus or plus, okay? So keep that in mind. All right, now, it could, there's another thing that it could do to become happy rather than get to. What's another possibility? Joe,
It could lose 6.
lose 6. How likely, which is more likely? Which is, do you think is easier for this atom to do to be happy? To give 6 away or to get 2? Mark, not Mark, Kyle, Kyle, my bad. Get 2, yeah, it's harder to give 6 away, all right? Any questions? So the valence of this is 2 minus, or 2, not, I shouldn't say minus, 2 negative, okay? Valence tells you how it likes to play with other atoms. What kind of atom might oxygen like to play with? What might be a valence of another atom that oxygen might like to play with? Nicholas?
An atom of 2 electrons.
To give away. A 2 plus atom. Alright? And sometimes it does. Alright? We'll talk about, come back to that a little bit later. Let's look at sodium. Sodium has an atomic number of what? Na. What's the atomic number? 11. Alright? I'm not going to put the nucleus, I'm just going to put the orbits. Because that's really the most important thing. Alright? So, let's put 2 on the first orbit. 8 on the next orbit. So it has 11. So 2 here, 8 here. How many have we used so far?
10.
10. So how many are left to put on the third orbit?
1.
Is sodium happy?
No.
No, it's very unhappy. Okay? Because this is not nearly complete. Okay, so what is the valence of sodium? What's the valence number? Let's just put the let's do the valence number. How many electrons does it want to give or get? William,
It wants to give away the 1.
it wants to give or get 1, okay? Now, when it does that, to be happy, is this atom going to be more positively charged or more negatively charged? Zach,
Positive.
positive, okay? Remember, this is not plus, it's not addition, okay? It's what its charge will be when it becomes happy. This might like to play with an atom that has what valence? Number and charge. This might like to play with an atom that has what valence? Mark?
7.
No. Vera?
1 negative.
1 negative, okay? An atom that wants to get an electron. And guess what? Here's chlorine, it has 17. There's 2, there's 8 more, that's 10. And guess how many are left over for the outer ring? 7, which means it's hungry for an electron, all right? Any questions? Now, this valence is 1 negative, because it wants to give or get, in this case it's get an electron, and when it gets that, it will be more negatively charged. It will have 18 electrons and only 17 protons that it started out with. Guess what? Sodium wants to get rid of this so bad, it totally gives it away, okay? Actually, I did put 7 here. Here's the 7th one, okay? And then here's sodium's electron. Sodium gives take it. It said, take the electron, okay? And sodium wants it so bad, it said, yeah, I'll take it, okay? So, here's an atom with more or less electrons than its number of protons. What do you call any atom that has more or less electrons than the number of protons? Brandon.
An ion.
This is an ion. It's written like this. It's a positive ion. It's going to be positively charged when it loses one of its electrons. This is also an ion. This is going to be a negatively charged ion. It's written like this, okay? But sodium and chlorine are attracted to one another now. Why are they attracted to one another? Ivy?
Because they each have the other needs.
Not exactly. This is happy to give its electron away, but still it's kind of like hanging out next to its friend. So it gave its electron away to its friend, but it's kind of like hanging out next to its friend. The fact that this is negatively charged, and this is positively charged, is the attraction. Okay, I just kind of gave you the answer away. Okay. What kind of bond would it be between atoms of opposite charge? Technically known as ions. Duh. Kiara, question or answer? -1. You gotta at least be paying attention to the questions. What kind of atom, what kind of bond would it be between two ions? What kind of bond would you call it if it's between two ions? Jasmine?
An ionic bond.
It's an ionic bond. Whoa, isn't that interesting? Okay, it's an ionic bond. All right, now, let's talk about bonds where atoms share electrons.
Oh my god.
Here's hydrogen. Its atomic number is 1 over there, okay? So, it's got 1 electron and 1 proton, okay? The electron is hanging out on its orbit. What's the valence of hydrogen? What's the valence of hydrogen? It's a number in charge. Well,
-1.
1, not minus.
Plus.
Forget about minus and plus. This is positive and negative, okay? Forget about the arithmetic symbols. Is it 1 negative or 1 positive? Matthew, my bad, Mateo.
Positive.
Positive? Because it wants to give an electron away and therefore it's just a proton without an electron?
No, which one's it?
It's both. Atoms that have a half-filled shell could go either way. It could get one or give one. It's not like this. This one, definitely, it wants to give one, my bad. This wants to get one rather than give 7 away. This one wants to give one rather than getting 7. But this could go either way, okay? So it's one of those atoms that could either give or get an electron. So when you're writing the valence for this, this would be 1 plus, or not, I shouldn't say plus or minus, positive or negative, okay? Kyle?
Can you have an atom without electrons?
Yes, you can. In fact, whenever you add something that in water that's an acid, it breaks up water molecules and takes away puts the electron somewhere else. Okay, so you'll have hydrogen. It's written like this. These are hydrogen ions. So if a solution of water has more of these than of these, and we'll talk about this tomorrow. We're not going to have time to talk about this today. This is the other part of a water molecule. So when you add something to water, and water molecules break apart into this ion and this ion, if there are more of these than these negatively charged ions, okay, then it's an acidic substance. It's pH3, pH2, whatever. All right. Now let's look at this. Even though it could get one or give one, more often it does give. More often it does give. And that's because there's only 1 proton here. Not much of attraction, okay? Now, this is 1. This is 2. Guess what? 2 hydrogens will share their 1 electron with 1 oxygen atom. So here's a hydrogen atom. Here's a hydrogen atom. Let me just put it here. And it shares its electron. These 2 share electrons with this oxygen atom. Okay, so you can think of this going here and this going here. Alright? They share the electron. What kind of bond is it where electrons are shared? Jonathan?
Covalent bond.
Covalent. Okay. Of those 2 bonds, ionic and covalent, which is the strongest bond? Benito?
Covalent.
Covalent, by far. Okay. Now, technically, for freshman biology, you say that they're sharing this electron. But when you get to chemistry, a chemistry class, they're actually sharing a pair of electrons. So, at a certain point in time, these 2 electrons are shared between oxygen and this hydrogen, and these 2 electrons are shared. And the reason why that happens has to do with centrifugal force. Electrons spin around in an orbit, okay, not exactly a circle, sometimes it's like this, but basically if you had just 1 electron going over here and going over here, you're kind of getting lopsided. But now if you got 2, it's kind of like you're balanced. Okay, so that's why atoms share pairs of electrons. Sometimes these two are kind of like fine opposites, so they're not like lopsided. You had one going like this. Understand what I'm saying? What the interpretive dance that I'm doing? Okay, it's kind of balanced. Okay, sharing pairs of electrons. But right now, for freshman biologists, think of they're sharing an electron. This is sharing an electron with this oxygen. This is sharing an electron with this oxygen. Most of the time, though, these electrons of hydrogen are hanging out over here. Can anybody guess why the electrons are hanging out over here? Cal?
Does that have something to do with, it's in the inner shell right now?
No.
Go with it.
Mira?
The oxygen atom has more protons, so they want
Yes.
more protons.
There's a lot of positive charge here. So that pulls those electrons over here. And because of that, and something else that I have forgotten since sophomore chemistry in high school, like 45 years ago, the hydrogens tend to hang out on one side and oxygen on the other side. It's kind of like lopsided. Instead of being like bisymmetrical, which is how I would like it, there's something, and I have to ask the chemistry teacher about this, because somebody had a problem with this in an earlier class. I can't remember why they're hanging out here, not like on opposite sides. But I think it does have to do with the pull of the electrons from all these protons here. Because of that, if there are more electrons here, that makes this side, what? Charge. This side. Here's the hydrogens. Here's the oxygen. If these two electrons from the hydrogens are hanging out more over here, this side would be what? Ivy?
Positive charge?
No. What's the opposite of that? Maria?
Negative.
Negative, because it's got like 10 electrons here and only 8 protons. Over here, there's just the 2 protons hanging out here, so this is more positive charge. This is a polar molecule. Water is a polar molecule, all right? It looks like this. And that makes it sticky to itself. Okay, so here's the negative side. Oops. Here's the negative side. Here's the positive side of this water molecule. This positive side of this water molecule would like to stick to which side of another water molecule? Cal?
Negative?
The negative side. It would be sticky to this. Okay? And that forms a weak bond. What kind of bond would you call that? What's the weakest bond? Of the 3 bonds you read about last night, what's the weakest bond? Cindy?
Hydrogen.
It's called a hydrogen bond, okay? I don't really like the term hydrogen because sometimes hydrogens aren't involved, okay? But oftentimes they are. Oftentimes, when hydrogens are bonded to other atoms, they tend to give away their electrons more, and that makes that side more positively charged. So that's why they call them hydrogen bonds. I would really prefer that they just name it polar bonds. So this is a bond between 2 polar molecules, okay? Now, there's a term for the stickiness of water molecules to itself. It's a word that means sticky. What's the term for the stickiness of water molecules to itself? Will? Cohesion. And then, this polar water molecule will also bond to other polar molecules, not necessarily water. There are other molecules that have a positive side and negative. So what's that called, the stickiness of water to other polar molecules? Letter.
A.
Alicia.
Adhesion.
Adhesion. Okay. Now, let's talk about why that water is important and the properties of water that have to do with it being polar. Okay? Water is a very good solvent, and it has to do with water being polar. Why is water a really good solvent? Because it's polar. What would be attracted to a positive side or a negative side to a water molecule? What would break apart because water molecules are attracting its positive side or negative side? That we just talked about like a minute and a half ago. Isabella? Ionic compounds. Chlorine would like to stick to which side? or the water molecule?
Positive.
Positive side, and so this side, okay? So salt, which is sodium chlorine, salt is made up of a sodium atom and a chlorine atom, breaks apart in water easily. Other polar compounds, a hunk of something that's made out of polar molecules, would also break apart because they're attracted to water molecules. Why is that good for life? Why is stuff dissolving in water good for life? Your body is like, I don't know, 70, 80, I don't know, it's a big percentage of water. Why is that good for you? What would you like to break down in your body? And water helps with that. Let me give you a clue. What would you like to break down so you could use the smaller parts that are broken down and released? Right now, you're in your body, you're breaking stuff down so you can use the parts. What stuff are you breaking down right now, and water's helping you with that? Kiara? Food. Yes. Okay. So water helps organisms break down stuff that they take in, so they can use the parts for building materials. Okay. Now, because water is sticky to itself, those hydrogen bonds don't break very easily, and because of that, water doesn't change temperature very fast. What good is that to life forms that we learned about in the previous chapter, prior knowledge connected thoughts? Brandon?
Homeostasis.
Helps with homeostasis. Okay. And that is also due to water being sticky to itself. What else? What other process that we learned about in the previous chapter, chapter 17, also is due to water being sticky to itself? Maria?
In the tropical rainforest.
The cycling, transpiration, water being sucked up through that straw. Any questions? All right. I think it's probably about time to go. Yes, it is. So, 2 things for homework. Redo the online quiz, which will include questions about today's material and also questions about yesterday's material. And also, I would highly recommend doing the first 6 questions of that lab page, because you are going to be working with just one other person. There's only going to be 2 brains.
What?
And then 3.